Hello, everyone. My name is Jade. I work for HPE, and I'm going to be talking about productive parallel programming. So we're in a room about HPC. There's lots of parallel systems everywhere, but sometimes they are harder to program than, say, a shared memory system. And you have HPC experts and you have users who may not be HPC experts, and to actually use these big systems is challenging. Everybody knows OpenMP for shared memory systems. This is like gold standard. It's great, but it's all compiler directive based, and it's just in C or C++ or Fortran. Yes. If you want distributed memory, you get MPI, SHMEM. Pick your favorite technology. You want both, you use both. Right? There's not one technology for both. And then we get to talk about everybody's favorite, GPU programming, and pick your favorite solution. There are many, 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 many solutions. But the one big thing is all of those solutions are not distributed memory. So if you want GPUs and distributed memory and shared memory, you kind of hodgepodge everything together, and that's your solution. And so you have to be an expert in each of these technologies. So I'm not trying to say anything bad about these. They're all good. However, right, they're all based in C, C++, Fortran, so you need to know C, C++, Fortran. Some of these haven't changed in decades. I'm looking at you, MPI. It's been around for a long time, but we're still doing things the same way we were 30, 40 years ago, long before I was born. You have to mix everything together, so you have to be an expert in everything. And if you want higher level abstractions out of C, C++, Fortran, you usually have to give something up. And so I say that HPC has a high barrier to entry because of all of this. Can we fix that? I hope so. So Chapel is an alternative for productive parallel programming. It's a modern parallel programming language. Portable and scalable, so I can run it on my laptop, I can run it on a supercomputer. Open source, like all good projects. It's hosted under the HPSF. And the goal is to support general parallel programming and making it productive at scale. So if I have a GPU or a CPU, I should be able to target it from Chapel, and I should be able to do that at any scale. So you should imagine a language that kind of has all of your favorite characteristics. I can read it and write it. It's performant, it's fast. I can scale up on my systems. I can target it, my GPUs, vendor agnostically, and I can be portable. And hopefully it's fun. Programming should be fun. If it's not fun, you're doing something wrong. And all of this is what Chapel is for. So let's look at some lovely code. You don't really need to read this. All you need to know is this is a benchmark. It's the stream triad. It's just trying to drive the memory system. And there's a lot of code on the screen to basically do one little thing and one little for loop that's doing a multiplication. And so there's a lot of boilerplate and a lot of fluff just to do that. This is not productive. Versus we pull in the Chapel code. This is the entire Chapel program. I can create my distributed array. That is, I create a distributed domain, and then I declare my array over that domain, and then I just write what I want. This is the entire program. You can compile it. It works. And so this is our productivity. What about the scalability? It does the exact same thing as MPI. So much less code for the same result. Another example, even more code for a slightly more complicated benchmark. This is the HPCC remote atomics benchmark. If you're not familiar with the benchmark, you basically have a bunch of remote variables, and you are updating them all, incrementing them all the time. The nice thing about this code is right at the top of the program, it tells us exactly what this code is going to do, and it has this lovely little for loop, and then you write a whole bunch of C to do that. I don't know about you. I like C. I don't want to write that. I'd rather write Chapel. This is not the whole Chapel program, but this is the core piece of the computation right here, is one single loop. This does distributed computing. This does shared memory, parallelism, all in one little loop. So that's pretty cool. Even better, right? So up on this graph is better. Chapel completely outperforms MPI in this case. And part of the reason for this is aggregation. So in this MPI, to get that aggregation, it takes a little bit more work. In Chapel, you sort of get it for free. You do have to add a little bit extra, but you sort of get it for free. And so you get much better performance with Chapel. Yes, I know that seems unreal. It's real. How does this actually all get to happen? There's kind of two concerns in Chapel. One of them is the parallelism, what you're actually computing with. So I can compute with a single CPU on a single node. I can compute with all of my CPUs on a single node. And we all love our GPUs, and I can drive the GPU. Right? So there's my parallelism. But I'm still only on one node, which brings in the other concept of locality, is where do I actually put my tasks, and where is that data? So I can have one task on one node. I can have one task on all of my nodes. I can have all of my tasks on all of my nodes. And, of course, I can have my GPUs. And then same thing with the data. I can just have the data on one node, and every single node calls back to the first node to see the data. I don't want all that communication, so I can replicate the data across all of my nodes. Or I can partition it so I'm not wasting space on each node. Each node only has the piece it needs. If it needs boundary conditions, it can just talk to the other nodes and get that data back. And again, getting the theme here, I can do the same thing with GPUs. So I'm not expecting everyone to be able to be Chapel experts at the end of this talk, but I am going to look at a little bit of the Chapel code here and kind of walk through how this execution is going to work. So all Chapel programs are going to start on locale 0. This is different than MPI, where everybody starts up at once. And variables are stored wherever you are. So in this case, we're on locale 0 on our current task, so that's where our array is going to be allocated. I can then run a serial loop over all of the locales, the nodes in my system, and I'm going to go through those nodes, and I'll move computation to the target locale. So in this case, we are moving to locale 0, which we're already there, so nothing really happens. And then, because we're now on locale 0, when we allocate a new array, so var b equals a, it's going to be duplicated on locale 0. And I can access it just like I would write a variable. I don't have to do an MPI call. I don't have to do anything special. It's just there. Then I can kind of go through all my GPUs, and I can move execution to my GPU just like I would move to a compute node. The GPUs are treated as what's called a sublocale. So you have your top-level locale, and that contains however many GPUs you might have. And again, right, the variable's in scope. I can access the variable and create a GPU array. So now B is my CPU array, C is my GPU array, and I've allocated the data. And I'll keep going through this program, just kind of walk through things. Right? I go and I move to the second iteration of the GPU loop. I move computation to my second GPU, and then I get my second GPU array. Notice that the GPU array disappears, the previous one, right? It's gone out of scope. It's no longer used. It goes away. And we continue over to locale 1. We move computation. We get our array, right? And we get our GPU array, and then our second GPU array. So all of this is serial. This is distributed computation, but it is serial. So this is one part of the feature set. The other part of the feature set is adding in the parallelism. So this is mostly the same code, and I'll call out the differences here. So instead of using a for loop, so serial iteration, I have this co-for-all loop, which is a single task, or it's parallel task per iteration. So every time this loop will go, I'll get a new task. So if I have 2 locales, the first co-for-all gets 2 tasks. The second part of this is I have this co-begin statement. So for each child statement, I will get a parallel task. And so that's how I can drive both the CPUs and the GPUs at the same time. All of this results in everything being driven at once. I have my GPU arrays, my CPU arrays. Everything's happening all at once, distributed and parallel. this is what I would call low-level Chapel. In Chapel, I want to be able to just write this declarative program. I'm not going to talk about this too much. Just know that we have this for all loop. It has this really fancy definition. All it means is the for all loop is magical and it gives you good performance. It will do the right thing. You can, write this simpler. This one's a little bit more easier to explain, right? But this for all loop, it's magical. It does the right thing. It will give me single node parallel computation when I give it a single node array. It'll give me distributed parallel computation when I give it a distributed array. And it will give me a GPU kernel when I give it a GPU array. All from one loop, all from one generic function, all of this happening at compile time, so without runtime overhead. And we have this lovely loop, but maybe I don't want to rewrite all of my code into Chapel. I want to use interoperability. So instead of calling Chapel code, I can call an external procedure. It can be C, Fortran, whatever. But it doesn't even have to be external. If you really, really want to, just write your C code in your Chapel program. It's just kind of a nice little feature. And then again, this is now working with distributed arrays, local arrays. The for all loop takes care of all of the communication, all of the chunking up of tasks, and then you can just do your math in whatever language you want. So I've kind of showed some benchmarks. Anyone can write a good benchmark. Let's talk about real applications. I'm going to talk about two today. Well, two ones at different ends of the spectrum, and then we'll get into Arkouda. Starting with the bigger one, which is CHAMPS. This is a 3D unstructured CFD framework, or computational fluid dynamics. It's very big. It was written by Professor Eric Landau at Polytechnic, Montreal. And the reason they want to use Chapel is because they can have students, undergraduate students, master's students, instead of spending most of their time learning how to write good MPI C code, they just write Chapel code and then they get good performance. They don't have that big learning curve, and so they can get right to doing science from the get-go. The other thing is that because it's performant, they're still competitive with other centers and other solvers, so they're not giving something up by using this productive code. On the other end of the spectrum, there's this biodiversity kernel. It's measuring coral reef diversity. Basically, this is just doing a whole bunch of convolutions, stencil code, over some images. It's a much smaller Chapel application. It was written by Scott Bachman and associated authors. And the reason why they were using Chapel is they were using MATLAB, and it was taking them months to do their code, and it was very complicated. So it was rewritten in Chapel, and they immediately saw performance improvements because they weren't using MATLAB. But the other thing is now that their computation was much more cleanly expressed in Chapel, they could actually do algorithmic improvements that they couldn't even fathom in MATLAB before, just because the code was easier to read. So they got algorithmic improvements on top of using Chapel. And then, because Chapel has GPU support, adding a little bit extra code, they could do GPU-enabled code. And they ran this on Frontier. And going from 4 weeks of a desktop run to 20 minutes on a handful of nodes, not only doing science much faster, but at far bigger scales than they ever thought possible. And this was with a very small amount of Chapel. So kind of two ends of the spectrum of productive applications. Again, why would you want to use this? Get out of the way of the science, just express what you want to say and stop worrying about managing the memory, stop worrying about the communication. There's many languages that are good at this, but to get that performance, you might have to give up those nice abstractions. In Python, if you want good performance, you're writing C. It's easier to write, easier to read, easier to maintain. You can get people started on your code earlier. You don't have to train them in a new technology. Well, you do have to train them in a new technology. You don't have to train them in a difficult technology, I hope. All of this leads me to Arkouda. Sometimes it's hard to get people to get out of their Python and their old ecosystems. So you want to reach people where they already are. And so you want Python at scale. So this is the motivation for Arkouda. You have people who already know how to use Python, but you also have these big problems that you need to solve. So Arkouda, there's kind of a lot of definitions for what Arkouda might be. Basically, you have a Python client, a Chapel server. They talk to each other. The Chapel server runs on all your nodes. The Python client is just NumPy or pandas. So you might say this is scalable NumPy and pandas. You might say it's a framework for driving supercomputers, right? We would like to expand this beyond just NumPy and pandas to insert your favorite framework here. That's all lovely and good. Performance is more interesting. This is a comparison against kind of competing technologies for Arkouda, like Dask and Spark, doing exploratory data analysis. This particular breakdown is of a workflow for telemetry analysis from Frontier. So they have a lot of telemetry data. They want to do science on it. And this is a breakdown of different steps in, say, a Jupyter Notebook. And we've kind of arbitrarily drawn this line of interactivity of about 2 minutes. So if you're waiting more than 2 minutes, your thoughts might have disappeared, right? So you want interactivity, you want results back quickly. As you can see in this graph, lower is better. For the most part, Chapel does a much better job. Right up front, you can see that Chapel is much slower because Arkouda is going to, Chapel Arkouda, is going to eagerly read in all of that data from Parquet files. But then once it's read in all that data files, it's just significantly faster to do computation. Part of this is because Arkouda joins across nodes are much more efficient because there's much better computation, because Arkouda is running on top of a built for HPC technology, Chapel, whereas Dask and Spark are not. The other thing that I will add to this is I did not personally run these results. The person who did knows a whole lot more about data science than I do. But they had a much easier time getting Chapel and Arkouda set up than they did trying to wrangle a Dask server and a Spark server. It was much easier to just launch the Arkouda server and do the job. So all of this, Chapel is built from the ground up for productive parallel computing. The language features let you express your computation, and it meets or beats the low-level approaches while still being, easy to read, understandable, maintainable, and without all of that extra boilerplate. The last thing I'll leave you with is this quote from one of the original authors of Arkouda. I was on the verge of resigning myself to learning MPI when I first encountered Chapel. After writing my first Chapel program, I knew I had found something much more appealing. Why would you want to write MPI when you could write Chapel? Chapel is open source. We would love to interact with you. If you saw something you liked in this presentation, please come tell us about it. If you saw something you didn't like, please come tell us about it. Come code with us, interact with us, help us make Chapel better for your particular use case. Thank you all very much. I'll take any questions now. So the question was, what's the out-of-core computing capability? Can you define what you mean by out-of-core?
How do you deal with massive arrays that don't fit in memory compared to Dask and Spark?
So Chapel does not, out-of-core by the amount of, can you put arrays that don't fit in memory to disk. Chapel does not provide a built-in ability to do this, but you can just take your array, dump it to I/O, and then read it back in. So there's no built-in way in Chapel to do this, but it's Turing complete language. You can do what you want with an parallel I/O to kind of speed up that computation. Yes.
Is it possible to check if there is any RDMA, remote direct memory access, implemented in your examples or even in Chapel?
So the question was, is there RDMA implemented? The short answer, yes. The Chapel runtime interacts with the various networks and will do RDMA for faster memory accessing. Yes?
So actually, related to RDMA, when you're doing the distributed work of pushing data and programs across all the cluster, are you doing any topology, like cluster topology aware optimizations live in the runtime? Does that mean you're detecting at source how big someone's allocation is on the cluster?
So the question is, are we using the topology of a given run to do any kind of optimizations? Answer is sort of. For the most part, we just kind of assume a heterogeneous or homogeneous allocation of nodes. So we're not doing any kind of dynamic changing of things. However, what you can do is say you have multiple NICs, multiple GPUs, and you want the locales to kind of splice them up. You can use something called co-locales and have multiple locales in a given node so that you can kind of divide up those resources a little bit more. But everything is still kind of assumed to be very homogeneous. Any other questions? Yes.
Does it run on the cloud?
The question was, does it run on the cloud? Yes. I have done testing on AWS using Parallel Cluster, pCluster. Works great. I know of some people who have used it with, I believe it was GCP. Worked great. I see no reason it wouldn't.
Possible to control the memory location, for example, on GPUs where the memory is loaded from scratch memory or shared memory on the GPU. Is it possible to control this with Chapel?
The question was, can you control where memory is loaded, particularly on the GPU? I mean, you can control which GPU it is, but like exactly where in the GPU, not totally. The one thing you can do is interop with CUDA, HIP, whatever, and do whatever they can do. Yes. So the question was, when you do something in NumPy, it's right. The NumPy operations are vectorized, but if you try and like not use those vectorized operations, it starts to get ugly. It's very similar in Arkouda. Don't try and iterate over an Arkouda array and pull all of your data from your remote node to your client. So yes. So the question is, when you're doing interoperability, does that included code get optimized by LLVM at the back end? Is that correct?
Yeah, basically, if we get this code, is it reinterpreted and optimized by the compiler, or is it called to like a DLL?
A little bit of, the question was, is it a DLL or is it like optimized by the compiler? Both. So the example that I showed specifically with that extern block, that's going to get optimized together. So there's kind of no extern calls. If you're calling out to like a precompiled object or a shared library, yes, there's like a foreign function interface passing between the two.
But the foreign function interface can be avoided if it's just simple numerics. If we don't call it, if we don't
I'm not sure I can answer that well. We can talk after if you want. Any other questions? All right. Thank you all very much.